Okay, I think it's better to start right now. Hello, everyone. My name is Oğuzhan Burak Tekin. I work as a senior HPC system engineer at EPAM. Today, I will be talking about use of HPC system in the world of data, or basically in the new terminology AI, data science, or other applications available in the market space. Today I'm going to introduce you how an HPC is, what is an HPC, how is HPC, what parts an HPC is made of, uh, how acceleration is provided on the HPC, including network storage, and how to use some applications on HPC, as well as I will be giving very small examples of running some Python applications on HPC system, and we are going to wrap up. Uh, Today's subject is what is an HPC, and in basic terms, an HPC means high performance computing, and high performance computing is the use of supercomputers and parallel processing techniques to run non-traditional works on a big scale. Usually we have laptops in our hands, but when we talk about the HPC systems, we are talking about something very, very big. Sometimes things were very unimaginable size. There are several characteristics of HPC systems, and if we just dive into some basic ones, and one of them is HPC systems do parallel processing. So whatever we run on the HPC systems usually go multi-threaded or can be distributed on multiple compute nodes at the same time. So this significantly reducing the time to require to process or execute the job on a computational system. HPC systems are quite scalable, and that means an HPC system can be consist of couple of servers or thousands of servers. So we will be talking about some HPC systems having millions of cores at the same time, running the similar jobs on millions of cores. On the other hand, because of the size of the HPC, the throughput is very important on the HPC system. And sometimes we run or work on very big data files, and sometimes we distribute the systems on multiple nodes. So interconnects between the computational nodes are very high speed. I'll come to that in the later slides. And in the HPC space also, there are a lot of specialized hardwares, especially we work with high performing or high frequency processors, GPUs, very fast interconnects to maximize the performance. So let's talk about how big an HPC can be. This slide is from HPC Top 500 list. It's a very current list. And at the first rank, you see Frontier HPC, which is in US. And if you look at the right-hand side, I tried to put the specs on this HPC. But in summarize, this device or this HPC is consist of in total of 4,400 different servers, each with 64 cores. In the backend, there is 700 petabyte storage, which is made of Lustre, and it has a very huge throughput. If you look into the details, this system consumes in total 21 megawatts of energy, and to cool this system, 22.7 meter cubes of water is flowed per minute to cool overall CPUs or the other parts of the HPC. So just imagine how much heat is generated in a system like that. And 1.2 exaflop computing power is achieved with this system. If you look at the details, and the total cost of this one HPC is just the capex part is $600 million. It's because of the size. But when you talk about the HPC systems, the size can be differs. And also there are right now different options like HPC on cloud. So you can use HPC infrastructure by pay on demand manner. So this is one of the examples, one of the greatest examples we can find today. When we talk about the HPC systems, we have to go into different functions of the HPC. This diagram shows the basic functionalities of an HPC system. If you look at if you are an HPC user, you first log in to the login nodes, and login nodes provides you to access to a very fast interconnect. And in the backend, you have a scheduler which schedules your job and distributes it to compute nodes, GPU nodes, memory nodes. And you use very big storage systems, usually parallel file system made of infrastructures like Lustre or BGFS or Weka. Also, you will have application space on an NFS system, etc. Also, there are other applications in the backend like a database to have a reporting or managing, or there may be some other infrastructure parts like monitoring system management, etc. In reality, this structure looks like that. I mean, if you look into actually this picture is diagram is showing different parts of HPC in cabinets form. And if you look at down of the picture, you will see that there are 34 computing cabinets and 17 storage cabinets in the HPC system designed for a specific use. Actually, this is a HPC system designed for a Euro HPC project in Western Balkans. And if you look at in details, there are InfiniBand switches, different types of servers and storage nodes, networks devices like regular Ethernet switches and InfiniBand switches for high-speed access. The ecosystem is very large on the HPC system, and the main blocks are quite different. If you it all depends on what you are willing to achieve and what you are going to design. But the main blocks of HPC system is the compute nodes or the server nodes and some storage nodes. There are different hardware devices for different purposes. For example, one with a higher frequency CPUs, one with a multiple GPUs installed, one with a lot of hard drives installed, or there are some storage blocks with hundreds of hard drives are installed, so it can provide you a very, very big namespace to work inside. Also, we talk about some accelerators like GPUs, FPGAs. On the other hand, we talk about high-speed networking and some other kinds of networking, especially for provisioning and management. And of course, another important part of the HPC is the cooling. And if you consider about the previous example that 25 megawatts of electricity is consumed, just imagine how much heat is coming out from the system. So the cooling is totally another project together done with an HPC system. Also, we have to look into the software ecosystem of the HPC. I mean, the software ecosystem usually consists of different components of different software. First of all, we consider of a provisioning system which enable us to deploy some applications or some operating system into the hardware we are having. There are some driver type of applications like OFET, which improves the performance on the InfiniBand interconnects. If you look at the other parts, one important part is schedulers. So schedulers are the piece of the HPC which creates a queue and runs the job on appropriate hardware and available hardware one by one. So there are different schedulers in the market. There is one important component which is providing a dynamic application environment, which we call environments modules. So it allows you to mod the application as a module so that the necessary paths are added to your application path or the login path dynamically or removed from your path dynamically. Also, HPC can be built of different operating systems like Red Hat, Rocky, Ubuntu, etc. Sometimes HPC can be hybrid, so you can mix up physical servers with virtual servers, or you can develop some part of the HPC with virtual functions. Also, it's possible some containers within HPC. Sometimes some services can be run within a container, like in an LXC container, or you can run an application in a container style, like Singularity is one popular container which is designed for HPC system. Also, without the software, of course, HPC is just nothing. So the compilers are very important. Programming languages are very important, such as GNU C compiler, Fortran compiler, etc., or Intel's packages like WANAPI, or other languages like Python, R, etc., are commonly used on HPC systems. When we look at the other parts, we have a specific, very specific subject to HPC, which is MPI. It means message passing interface. Message passing interface allows a job to run on multiple servers. So messages are being passed through one server to other server. So each server can run a small part of the same job on multiple cores. So there are different versions of MPI. So application, whatever application you are using, we usually look into the MPI supported with that application. Also, there are some backend applications which manage the HPC systems or get the reports from the HPC systems, because utilization of the HPC system is very important. An underutilized HPC is just spending electricity for vain. So you have to understand how the HPC system is utilized, who is utilizing that. Sometimes the jobs are being sent in a wrong manner, so they have to be corrected, etc. When we look at the storage part, there are different parallel file system options and distributed file system options. There are some popular ones like Lustre, BGFS, Weka in parallel file system space. And also, if you are running some other distributed file systems, Ceph and IBM Spectrum are another option. So we improve the HPC system with different sets of tools. So we have, for example, Open On Demand, which provides a web-based GUI access to HPC system. We sometimes add firewalls so that HPC can be secure from perimeter side. We need to have some authentication mechanism. So sometimes we have hundreds of users running on the same HPC system. So we definitely need a central authentication system. So we do need different kinds of databases, reporting, etc. So the ecosystem is very large. By the way, I haven't come to the applications being run on the HP system. There are millions of that. This is just the ecosystem behind an HPC. To give a brief idea of what HPC is looking in the backend. So switching from this side, first of all, some parts of applications are libraries. There are different libraries for different purposes, especially math libraries are very popular if you are running a scientific application. Also, depending on the code you are working on or the code you want to run on the HPC, you need different compilers to compile the applications or develop your applications. I mentioned the MPI. I also, let me give a brief idea of where HPC is being used, the scientific applications, engineering applications, finance applications. There are millions of them, and each applications has its own kind of needs. So whatever you are going to run, you have to design the HPC system depending on the application you are going to use. If you want to work on an HPC system, first you need to know the details of the HPC the application. So how you can integrate that application into an HPC system. There are lots of good examples. If you search on the internet or there are people working on the same applications or the vendors are providing a lot of information about how to run their applications on the HPC systems. Let's switch to another important part of the HPC, the acceleration part. When we talk about the acceleration of the HPC, we usually talk about the GPUs. And what is a GPU? GPU is a general purpose graphical accelerator unit. Basically, a CPU is a SIMD device. SIMD means single instruction, multiple data set. CPU is a SISD device, single instruction, single data set device. So you have one core, but one core only work on one data set at a time. But when we talk about the GPU is a SIMD device. It means single instruction, multiple data sets. So you can have a part of the you can have an instruction and you can apply it to a part of the data set, and you can divide the data set into chunk, and you can run it on the different parts of the GPU cores. So at the end of the day, each GPU gets a subset of data, and they run a similar code on the cores, and at the end of the day, those outputs are combined together to form a big result. GPU acceleration on hardware has different aspects. I mean, in the last couple of years, we had the GPU cards installed on the PCI device or server hardware. So each CPU has a certain number of PCI lanes. So behind those lanes, there is a PCI switch, and GPUs used to consume some of the lanes available on the PCI switch. So this usually created a bottleneck between the GPU to GPU communications on a older generation of hardware. But recently, right now, GPU vendors are providing their own motherboard type of hardware. So very similar to multi-processor CPU motherboards. these GPU motherboards are connected into a server chassis, and they communicate. All the GPUs on the those motherboard communicate with each other just bypassing the PCI Express switch. So they have their own communication. So all the communication between the GPUs right now happens much, much faster than before. So this has bring another level of acceleration to the HPC system and for the hardware used on the HPC systems. And the communication has different approach on the HP system. First of all, there's a concept called RDMA, Remote Direct Memory Access, which is a technology allows the hardware to access the server memory bypassing the kernel and CPU stack. So application running on the memory can communicate with the hardware device like host channel adapter, which I mean by, for example, InfiniBand adapter, much faster. So there is no overload or overhead on the CPUs while making this kind of communication. And also, it is possible to use other libraries like NVIDIA Collective Communication Library, in short called NCCL. It's possible to create an environment to communicate across the GPUs. So this allows, especially if you are running an AI model, for example, this allows multiple GPUs can share each other's memory and can with that you can run bigger models on the HPC systems or a single server. Let's switch to another technology being used by HPC system. Actually, this is quite alike like the RDMA, but this allows GPU Direct allows communication with the third-party device with GPU in a much faster way. In the regular case, those communication takes through over the PCI Express lanes, PCI Express switch, but with GPU Direct RDMA, the third-party device and GPU can communicate with each other much faster. So it means you can communicate from InfiniBand interface to GPU just bypassing the CPU resources. So this can also bring additional advantage. So when you work on multiple nodes, you can also communicate from one GPU on one server to other GPU on another server by bypassing the CPU mechanism. So you can just communicate through the GPU direct over RDMA to reduce overheads in the communication. Also, this can be extended for the storage. It's a newer technology. So if you have a storage like NVMe on a hardware, on a server, GPU can talk directly to the NVMe storage just bypassing the CPU. So you can read or write your data much faster, unlike the traditional way. And another part which actually makes the difference on the HP system is the network. The most there are basically three ways of communicating compute nodes and servers together. You can use Ethernet, but there will be a lot of TCP overhead when designing an HPC on Ethernet. There is one technology designed by Intel, but it's not very used. And more common communication method, actually it is also similar to InfiniBand. most common communication technology is right now InfiniBand, which is used on the HPC system. And this is the roadmap of HPC system. Currently, we are on year 2024, and we are really talking about 800 gigabits per second on a single port of a switch. So you can interconnect the switches together at each port at 800 gigabits per second, or you can have multiple ports on the server hardware, so they can speak to InfiniBand switch at different speeds. I mean, I worked on a project, and with that project, each server had 8 InfiniBand adapters. All of them were talking at 200 gigabit per second speed. So in total, this was an AI project, and each server achieved speeds 1.2 terabits per second per server hardware. And it's very possible to combine these switches in mesh topology. When you design an HPC, it can grow into hundreds or thousands of servers using this kind of infrastructure. So in the upcoming years, of course, we are waiting for much higher speeds. I mean, currently we are talking about the XDR. On the next years, we'll be talking about GDR and LDR speeds as in the roadmap. Okay, so the another important part is the storage, because when you deal with the HPC system, sometimes you deal with petabytes of data, and petabytes of data sometimes being stored in a single namespace. So to achieve that amount of huge storage spaces, we use parallel file systems, and one of the most popular ones is Lustre. Lustre has been in the market for many years, and it's open source. These parallel file systems consist of different layers. For example, a management server is manage all the nodes in the system, and there are metadata pairs which actually works like address books of the chunks on the parallel file system. And there are the object storage part, object storage servers, which consist of servers plus some storage devices together. And these are like the works like the object storage part of the parallel file system. So they store the chunks of data. So when we design an HPC, for example, this is a schematics of a Lustre system which has been designed for a petroleum company, petroleum research company, and the total capacity of this storage system was 6 petabyte. So it was very huge, but also it is possible to design HPC system, storage system much bigger than this in the same mentality, in the same manner. So on the HPC system, the data grows, and data grows very fast, and sometimes you need to access the files very fast. Therefore, you also need to distribute the files on multiple storage systems at the same time. So this is one of the tests we did on the typical Lustre system. We run parallelized tests. So we use multiple nodes to run synchronous write and read at the same time. And if you look at the details, we have achieved something like 44.7 gigabyte read per second and 36 gigabytes per second write on the same system. So, by the way, these are modest number, and the previous example was totally on the spinning drives, the regular SAS-based hard drives. But if you use newer technologies like SSDs or NVMEs, you can get much higher throughput in a very smaller architecture. And there is an example of that. This is a NVMe-based parallel system example based on BGFS, another parallel file system designed by Fraunhofer Institute of Technology. It's a technology institute, but because of their HPC needs, they designed an parallel file system and they made it open source. And we regularly use it on different projects. In this example, there are multiple storage targets. In the previous example, for example, we had more than 72 storage targets made on regular RAID devices. But in this one, we have NVMe storage targets. Actually, the number of the storage targets are not high as the previous one, with just 6 storage targets based on NVMe. We made some throughput test, and on single storage targets, we achieved more than 24 gigabytes per second throughput. And if we run the same targets, for example, on single and multiple uh, object storage object targets, we achieved an interesting result like this. On the left graph, a certain amount of file has been written onto disk. And as you can see, it first goes to cache, so the throughput is very high. Then cache is consumed by writing the data into the regular drives. On the very left example, we write the same data on multiple target at the same time. So we parallelize our writes on the storage. So if you look at that, each storage has used their cache. And by the way, in two example, same amount of data has been written on the storage. So since the data writing is parallelized, it took much less time to write the total amount into the same storage. So if you look at the numbers or the performance results, we achieved something like 64 gigabytes per second writes on 3 storage targets, unlike the one on the single storage targets test. In single storage target, we had something like 24, but in 3 storage target, we achieved 64 gigabytes per second. This is the power of a parallel file system. If you increase the number of storage targets, you can even get much higher throughput on a HPC storage system. That's how the parallel file systems works on the HPC systems. Let's switch to the applications part. So here's the example of I want to give. The scheduler is one of the important component. As I explained in the earlier, scheduler is the part which takes the job, puts into a database, looks for the resources, and runs the jobs on appropriate queues or hardwares. So just if you look at the screenshots, you will see some compute nodes or partitions available on the system. Some of them are allocated, some of them idle. And this is how a scheduler runs the jobs. They choose a available server, available compute nodes, and allocate it and runs the application on that specific hardware part. And if you submit more than processable jobs waits in the queue, and when the hardware became available, they starts one by one as the hardware became available. They run and they complete it depending on the size of the job or the resources required for that job. So this is why the scheduler is important for the HPC because you have hundreds of users, you have limited resources, so everything have to be put into queues to provide a fair share of usage. And as I mentioned before, there are different types of ways to use or run the applications on the HPC. First of all, we install the applications as other applications. We install our computers to the HPC, but we use specific paths on the HPC systems, and we create modules for that applications. And for that reason, we create a module file. For example, in the upper side, you will see an R installation, RStudio installation. If you look at the directory structure, it is just a standard RStudio installation. If you consider the folders. And the module file just defines where is the binary paths, where are the libraries, where are the menus, etc. And do I need to have additional modules to be run with the same application? For example, RStudio requires Qt libraries and R at the same time. So when we load the RStudio, we also need to include Qt and R at the same time in the running environment. And as the applications space grows, I mean, you can have different versions of the same applications. Also, you can have hundreds of different applications installed in the application space. For example, if you look at the OneAPI versions, there are two versions of OneAPI installed here. And if you look at the BeanUtils, there are multiple versions of BeanUtils are installed. So environment module provides the dynamic application environment, which also allows uh, multiple versions of the same applications to be installed without breaking the libraries. That's another important part of the HPC. And we just load the modules. So we see all relevant modules are also loaded with the same modules. So we can create a working environment with just several commands. And it's also possible to create, I mean, we are talking about Python worlds, so we usually use Conda environment in HPC systems. So we create a mini Conda environment, we load it as a module, and in this example, we create a Bioconda-like environment for molecular biology researchers. So if you look at the specific environment we created to that group, you see a lot of molecular biology applications. So it's possible to create multiple virtual environments for different applications or different groups working on the same HPC systems. And it's possible for them to use these environments within their batch files, which are important to submit jobs to HPC system. For example, these tools are used for genome alignment, and also we can use container applications. As I mentioned earlier, there is a very good containerization tool called Singularity. You can import, you can create Singularity containers by yourself or import Docker containers or other containers into HPC environment. And this, for example, container was running Brief, which is a deep learning tool. So it's possible to integrate multiple applications for different purposes into the same environment without any problems. Another important thing is with the HPC is the parallelization. I mean, most applications written in Python are single-threaded applications, and to get the best performance from an HPC, the applications should be written in a multi-threaded way. And if the application is also written to use MPI type technologies, the job can be distributed to multiple compute nodes at the same time. For example, here we have 15 available nodes on the HPC system, and on the right-hand side, we create a batch file, which is a file we use to submit a job into a scheduler. And if you look at the batch file, we define the resources, account, etc., how many threads we are going to use, how much memory we are going to use, number of cores we want to use, etc. And we load a module, which is WASP in this case, and we run a application in a distributed manner with the command like MPI run, which means run the applications on the MPI environment. And the results becomes like this. Application sees that there are, for example, in this example, we choose 8 separate servers providing 128 cores. And the application's output is like that. It takes the 8 nodes as defined and also finds 128 MPI ranks, which are the threads basically. So it starts to run. So that has to run the same job one divide 1/8 of the time that can be run on a single server. So we run the application much faster by distributing the application to multiple servers. This is how the distributed parallelization works on the HPC. And this is the output we are getting from an application like this. And if you look at another example, I mentioned about containers. Containers is a way to provide both backward compatibility and forward compatibility in a HPC environment. For example, in this example, the operating system is Rocky Linux 8.8, which is a same release of Red Hat 8.8. And inside the container, we can see another version of operating system. In this case, it's a Debian Linux 12. It's a very recent operating system. Because the newest version of application we want to install on the HPC either cannot be compiled on the HPC system, or it required a lot of libraries which we don't want to install on the HPC system, or sometimes we don't have the right code to run the application or compile the application on the specific operating system. That's why we use the containers in one hand. And with the single command, we create a batch file like Singularity exec, the CIF file, which is created by Singularity, and the command inside the container. And we can also add the parameters if you like. And the latest picture here is the latest screenshot. Is after we load the container, we run the application, and which is actually running in a temporary sandbox in a container, and we get the graphical output as we are using a Debian operating system. Actually, we are running on a Red Hat version, Red Hat variant, which is Raki 8.8. So this is one way we use the containers, and there is another way of.
Just like we are exceeding time already.
Okay, I'm
Thank
going fast. Thank you very much. And another way is using the parallelization in containers to use the backward compatibility. And in this case, the operating system is Red Hat Raki 8.8, but the container is CentOS 7, which is an older version. Because of the compatibility of the application, in this case, customer required an application which is not suitable to run on the recent operating system. So we create a container, and we are able to run the old version of application in the recent operating system. And this case is from a company who is designing turbofan jet engines. And there are other things. I mean, there are lots of backend functions on HPC systems. And these, if you want to summarize, we need to consider security, storage function, network function, authentication element, all the list. I mean, there are lots of applications running in the backend just to provide the smooth work of applications on the HPC system. And I will give small example of how to run Python. This example is to create a Python code to run primes between 0 and 1 million. If you look at the code, this code is just to run on single core. So it will take quite a time to run this code. If you want to parallelize this code in a multi-threaded version, we need to load several libraries like threading, so that we can create threads and create chunks of the algorithm to run on multiple cores. And that's how we change from single thread to multi-thread for the same purpose. And also we can use other tools like NumPy, etc. And we can use GPUs and we can use multiple nodes at the same time to run the same jobs on multiple servers using multiple cores. This is the way a Python code should be changed to run on multiple servers so that we can get the results in a much, much faster way. So we run it with a command to run on the MPI with MPI exec or MPI run. And here we come to the end. This is the same version to run on another version to run the same code on GPUs. So running the CUDA running the same code on GPUs requires addition of CUDA libraries, etc. So you can run the same code on the GPU as well, just changing the basics. And we can use a batch file again to submit the job to multiple GPU HPC system like this. To wrap up, on our HPC systems, we need fast interconnects. We need to utilize communication protocols. We definitely need to use purposely designed HPC storage systems. We need to understand the benefits of HPC systems. We need to look into parallelization so that we can parallelize the application we want to develop. Also, if there is acceleration available on the system, we need to learn how we can utilize, how we change our code to utilize the acceleration. And we need to, of course, learn how to develop our applications in the HPC way. That's the whole thing. Thank you very much for your time. My communication details are like this. If you want to send me email or get in touch with me on LinkedIn, feel free to connect. Thank you very much. If you have any questions, I would like to answer.
Thank you so much, Oğuzhan. It's a very tough topic, and thank you for managing to share with us all within 40 minutes, 45 minutes. And I am very congratulations you also. You learned that hard topic. It comes to the same as learning C and being expert and learning HPC and being expert. Thanks a lot. And like Oğuzhan mentioned it, if you have any question, please raise it and we can answer. If no, we can move on our next